Do you guys know who was given credit for the theory of plate tectonics?
Oh, that's not those two.
Not those two.
It was in the book. Remember that? I can't remember what his name was though.
Is that like one of the 50 smart people you always hear about? Okay. Isaac Newton?
No. Alfred Wegener is his name. But there's a lot that happens before and after him that actually gives like the full picture of plate tectonics. So one of the guys I'm going to highlight is Abraham Ortelius, which was clear back in 1596. And he noticed that the coasts of South America and Europe fit together. Have you ever looked at a map and kind of noticed that too?
Yeah.
Kind of a weird coincidence.
I think they told us that since like third grade. I'm guessing. I know I've heard of it since elementary.
Plate tectonics get taught quite a bit, I think. But and then he proposed that they had been separated by earthquakes and floods. And then later on, like 200 years later, Edward Seuss noticed that the late Paleozoic plant fossils in India, Australia, Africa, Antarctica, and South America matched up. They had like patterns that reached all the way across the continents. And then he phrased.
So since 1885.
Huh?
They've been finding fossils since 1885.
Yeah, it's kind of hard to think of that stuff. And then he coined the phrase Gondwanaland. Have you heard that before? Reading the book or
Gondwana, but not land.
So that was like the previous name of Gondwana. And then he thought his theory was that land bridges connected all continents. And does that make sense? Because if there would have to be land bridges, then that means that there's less water. So that doesn't really make sense.
Unless the ice land bridges.
Unless there was a lot of ice. And the top picture is Abraham, and the bottom is Edward.
I don't know why, but that reminds me of a movie where that guy was like, a guy that looked like that was really mean.
Yeah, he has kind of a severe look, but that's okay. I'm good enough. And then the next guy was Antonio Snyder Pellegrini, and he also noticed the coasts of the land masses matched up, and then he drew maps. That's something that he did different. And then he also cited fossil evidence. And then he thought the continents, his theory was that continents are getting separated by the Earth getting bigger, which is an interesting concept. And then the next guy, clear in 1910, was Frank B. Taylor, and he theorized that mountain ranges, the Andes and the Himalayas, were created by the fusion of Earth's crust. And does that match with what we think now? Because the Himalayas were created from India smashing into Eastern Asia, right? Okay.
I just have one question. When was Antonio Snyder?
I don't remember. I didn't put that date on there. It's not important. Are we good?
Yeah.
Okay, now we get the guy that gets all the credit for it, and his name is Alfred Wegener. He's German, and he came up with the idea of continental drift, and he used the continental shelf outlines to match the outlines of the continents together better. And everybody else before him just used the outlines of the land masses instead of the shelf outlines. He came up with the idea of Pangea, what is Pangea? Based on
No, I think it was the last supercontinent.
The most recent supercontinent, yes. In his mind, it was the first and probably only supercontinent. But we know now that there's been Rodinia and then a couple others before that. And then he used all the evidence from the previous scientists for like fossils, rocks, geologic formations, and glacier formations to come up with the idea of continental drift. And he was not able to provide a mechanism, so his theory was not accepted until after he died.
Poor guy.
I know, he didn't get
Did
credit.
he only do continental drift?
Yeah.
That's all he's about?
I think so. That's well. He was also he also studied glaciers. He was very big into glaciers, so he probably had a lot of findings in glacial deposits
I
and
don't
stuff.
know why, but his face looks familiar.
Yeah. You've probably seen him a lot in school. Okay. So after him, Arthur Holmes came along in 1928, and he came up with a mechanism called thermal convection, which we've learned about that in our readings. And you guys want to explain convection or give it a shot?
Convection is when cold water heats up, goes to the top, and because of the wind, it's cool up there, so then it cools down and sinks back down and heats up and repeats.
Yeah.
While doing that, it also takes dirt and other things with it.
Takes crust with it, yeah. And then after Arthur Holmes was Alexander de Toit in 1937, and he noticed that the coal deposits were present in cold climates. Does that make sense that coal deposits were present in cold climates? It does? Like, would there be tropical plants in a cold climate?
No.
No, there shouldn't be.
Well, then again, I've heard Antarctica was found warm climate stuff.
Well, that's also part of plate tectonics because Antarctica wasn't
Yeah.
always on the South Pole. And then he determined that Pangaea split into two subcontinents, which are Laurasia, which would be part of North America, and then Gondwana, which we've heard the Gondwana land earlier in this lecture. So here's just some evidence. Continental fit. You can see all the continents kind of line up on the coast.
That only brings me to one question.
Hmm.
Why? So it doesn't have to be all the land masses together to make a supercontinent?
I think most of the time it is considered that, yes. Like all the land masses together, or a very majority of them.
So why couldn't we say America and Europe are super land masses right now today? Supercontinents.
No, because they're split apart from the bigger whole.
Well,
We consider like a supercontinent Pangaea, so we can't also consider North America.
well, you just said it about Loretta and
They were
Gondwana.
subcontinents.
Subcontinents. So that's what America and Europe would be?
Yeah.
Okay. That's what I was trying to figure out.
Okay, and then after continental fit, there are rock sequences, and the different colors of the rock notate the different rock sequences. You got the brown that's all in Africa and South America, a little bit of green down below, and then this yellow color that's in North America and Europe. And then mountain ranges. Have we heard of this theory before?
Kind of.
Yeah.
Kind of, yeah. So the Appalachian Mountains also match up with the Caledonian Mountains that are up in Ireland and Scotland area. And then these mountains right here, these are called the Atlas Mountains, and they would match up with the lower part of the United States. Okay, glacial evidence. So I don't know how to run this, and if you don't go the right way when I'm trying to get to go that way. So glacial evidence, there were evidence of glaciers all up in this area.
Mm-hmm.
And this is Antarctica, South America, Africa, India. What's that? Okay. Fossil evidence. There were fossil remains. This cyanogathus. You gonna?
There's arrows on the bottom you can click to.
Thanks. Fossil evidence of cyanogathus is both present in South America and Africa, which would have to mean that either it was present on both land masses when they were split apart, or they were together at one point. And that's the same for Mesosaurus, a plant called Glossopteris, and then Lystrosaurus. They would have to be connected somehow so these animals can move to the different continents.
I wonder how smart the board is because I have an idea for you. You could wear like one hand has a glove, the one that you point with. Because my phone is too stupid to recognize I'm just wearing a glove when I'm in the cold weather. So I can't use my phone until I take the glove off and freeze my hand off.
I
So
don't
that's
know.
an idea.
Technology normally doesn't like me in general.
Yeah, I have.
I should just be doing notes on the board. That's easier. Okay,
Mr. Target's now on board too.
so that was some evidence of plate tectonics. Now let's go to the more recent evidence for plate tectonics, and that includes paleomagnetism, which is the study of magnetic fields frozen in place within rocks. And the rocks that they are frozen in place in are igneous rocks, and these igneous rocks contain magnetic materials that align with the poles on Earth. Do we know what igneous rocks are?
Igneous rocks are the ones from lava and magma.
So lava rocks, basically. And then when igneous rock comes up into the crust, it freezes. And then if that igneous rock contains magnetic materials, then it freezes in line with the North and the South Pole. So their magnetic domains align, is what that's saying. And then those rocks that are frozen in place don't change unless they get remelted again. And so they provide a paleomagnetic record of Earth. These flips, and the Earth can flip in their magnetic fields, and the flips cannot be predicted, and they're caused by magnetic elements. Did you have something to say?
I was just gonna say, how does that happen with the magnetic element?
It's something to do with the core, because the core contains iron and nickel, and they're both magnetic elements. I actually did some research on that because I was never taught that, and I can't really find. I
So
can't find much.
basically, we can just say the core is basically a lava lamp in the middle of the Earth, and that's what causes it.
Yeah, that with convection, yeah. And these elements get pushed onto Earth's surface at ocean ridges and create evidence for Earth's historical magnetic fields. Magnetism, physical phenomenon caused by the spin of some electrons in electricity. Magnetism is created by electric domains or magnetic domains. So Earth is dipolar. Do we know what dipolar means?
Polar two ways.
Yeah, what does di mean?
Two.
And then polar is opposite. So there's a south and a north pole. Right now we are in normal, which do you guys notice anything about the north and the south pole?
It's upside down.
It's upside down. So we call this the North Pole, but it's actually the South Pole because when we use compasses, the North Pole is attracted to the opposite side.
So, if you use a compass, it's pointing south now?
No, it's pointed north.
Okay.
Like it's pointed this way.
Okay.
But you're using the opposite pole to attract it to the South Pole, so you'd be using a North Pole.
Okay.
In your compass. And then when it's reversed, which the Earth has done several times, it is actually the North Pole and the South Pole.
How long does that usually take to reverse?
It can't be
just
predicted.
random?
So it's random, yeah. It hasn't switched for several 100,000 years, like 750,000 years, I don't think. So it's been that way for a while. It might switch one day. Hopefully not in our time, but it might happen. So.
What would happen if it did?
Well, your magnetic field has a lot to do with protection from UV rays and stuff, or sun's rays. So if it has to weaken first, and if that weakens, then it's going to affect our life because it's going to give it, less protection on Earth and everything.
So would it mess with electronics too?
It probably would, yes. Like aurora borealis. Have you guys ever seen those? Those are colors and magnetism and all that stuff. So it would change that. It would change protection and all this stuff that's kind of important. It wouldn't change too much, but it would have to change. So there are several instruments that we have developed to help study the Earth's floor, and one of these is a magnetometer, and that is a device that can detect small changes in the magnetic field. That's a magnetometer, and they send it down to the bottom of the Earth, or the bottom of the ocean on a cord, and it detects magnetic changes.
It looks like a missile.
Yeah, that's kind of what I thought when I saw it too. And then another one is sonar, and this is a picture of sonar. It sends pulses down to the Earth, and then however these pulses land on the ocean floor, it sends back the pulses. So you can see the different types, or the different heights and depth in the ocean topography. So this is a isopron. Do you guys remember what that was based on? That was a vocab word.
I read that.
Anyways, in an imaginary line on a map that shows points that have the same age, they formed at the same time. So
Yep.
basically, all the red formed at the red, the green formed at the green.
Mm-hmm.
Right?
Yeah.
Okay.
So this red would be older than 11 million years ago. And then this blue stuff, which is not very many of, would be 180, like 180,000 years.
Where's 180 million years?
Well, yes.
Oh,
Because
so
it's-
it's backwards.
Yeah, it's backwards. Oh, this is the newest crust that's formed along these ridges, and then this is the oldest. You don't see that there's very much blue, and why would that be oldest?
Because the crust is always, the oceanic crust is always making new.
Yes.
Or it could have been directed by Thea, right? Or
No.
no? The planet that collided with the.
I don't think that's what that's showing. It's showing that, okay, when you're making new crust in the ocean, the old crust has to go somewhere. So the old crust would go back down into the mantle and get convected.
So does that mean the dark blue places are the lowest places? Most
Yeah,
often?
theoretically, because older means denser, which means deeper. That would make sense. Okay. No. This is a very blurry map if I can get back to it. But this shows the magnetic reversals on Earth along this black part is a ridge, or this red part is a ridge in the ocean. The purple, the blue, and the green are normal magnetic times, and then the ocean colored stuff would be reversals.
Hey, that looks familiar. I don't know why.
Yeah, well, that's the mid-Atlantic ridge. You've probably seen a map of it somewhere.
It's because that's what I'm studying.
Yeah.
For the project.
Iceland and Greenland. So, plate tectonics. The theory of plate tectonics is born based on all this evidence that we've learned about so far. And the mechanism for continental drift, which then became plate tectonics, was found based on sonar and magnetometers. And then the theory of plate tectonics, I'm going to write this down. Earth's solid outer crust, the lithosphere, is divided into plates that move over the semi-liquid upper portion of the mantle, the asthenosphere. Okay, so here's a little video of Pangea splitting apart. Just to see what happens. You see India smashing into Asia.
Yeah, moved a long ways.
Hmm?
Moved a long ways.
It did, yeah. And Australia also moved a long way. And he moved clear across the globe almost. So, convergent, do you guys know the types of plate boundaries? Convergent, divergent, transform.
Oh, yeah, I'm gonna keep it down.
Want to define them when we get there?
Divergent is going apart.
Yep.
Convergence is where one goes over the other one, transform.
Mm-hmm. Transform slides past each other. Okay, so area where two lithospheric plates move towards each other and collide or convergent. Divergent, two lithospheric plates move towards each other. Or they move away from each other. Yeah. Got that wrong on that one. And then transform, they slide past each other. Okay. Within continental plate boundaries, there are three different types of convergent plate boundaries, and that's continental. You guys want to take a gander at what continental means?
Continents rocking each other.
Yes, two continents colliding. They often make very big mountain ranges. As a diagram of it. And then continental oceanic.
Ocean collides across
Yes.
or continent.
Yes. What would be an example of this? Continental.
Himalayas.
Himalayas. Yes. India and Asia smashing together. What would be an example of this one? Continental oceanic.
California.
Yeah.
Yep.
I was gonna say this.
And then the North American plate smashing into the Atlantic. And then the oceanic. You guys have an example of that one?
Indian Sea to Atlantic Sea. Ocean. Indian Ocean.
Oh no, I wasn't thinking of that one. It might be. I was thinking of like the Ring of Fire right along Asia.
Oh, I know what you're talking about, yeah.
So there's a rule with convergent plate boundaries. The denser or heavier plate will always subduct beneath the less dense plate. So I would write that down. And then some things that might form on a convergent plate boundary is a subduction zone, and that is a site where one plate edge descends into the mantle. And then a trench is a long, narrow valley on the seafloor that forms oceanic plate boundaries. So an example of that would be the Mariana Trench.
You know, if we wanted to smooth out Earth, we should just put the Himalayas in that trench.
Actually, I don't think that would work because the Mariana Trench is deeper.
Yeah, but it would slightly smooth
It
out
would
Earth.
slightly smooth it out, yes. It'd still be a massive cavern, but. Okay. And then a couple more forms that might form based off of convergent plate boundary is an island arc, which an example of that is a Hawaiian island, and which you're doing on your project, right?
Mm-hmm.
Yeah. And then a volcanic arc, a belt of volcanoes formed from the oceanic continental plate boundaries. And that is Yellowstone and all the Cascades. There's several volcanoes that are in the Cascades. Just most of them haven't erupted for a very long time. So most people don't know about them. And then partial melting is selective melting of solid rock based on mineral and melting temperatures. So that happens when the subducting plate, which is the denser plate, is subducted into the mantle, and then it reaches the point of melting for its rock. And then it comes up and it creates volcanoes.
So you're saying there's volcanoes around California that have also laid dormant?
Yeah. Well, I don't know if it's necessarily California, but it's close to the Yellowstone. Yeah. There's a lot of them. Just look at a map of volcanoes, dormant volcanoes in California, you'll see a lot, or Western North America. So, divergent plate boundaries, you got continental divergent plate boundaries. And that's when two continental plates are separating from each other. And then you have oceanic, and that's when two oceanic plates are separating from each other. Yep. And that's what you're doing in your farm, right? Yep. And then rule, new material is less dense and becomes more dense as it cools and ages. Write that down if you don't have it. If it's less dense, what does that mean?
It floats.
It floats, it takes up more space, yeah. And then some formations that could form on a divergent plate boundary is an oceanic ridge. That is shown here, kind of like an underwater mountain range. An example of that would be the Mid-Atlantic range. And then seafloor spreading. Oceanic crust is formed by rifting in the seafloor. Rift Valley, lowland or depression formed by the splitting of tectonics or faults. Red Sea, Rio Grande River. So those would be continental plate, divergent plate boundaries. Okay, transform plate boundaries. These are the ones that are very confusing to a lot of people, so that's understandable if you don't get it. And then a fault is a planar or angled fracture in the rocks under its crust, and is caused by compressional or tensional forces on either side of the fracture. So what does compressional mean?
Together.
Pushing together. Tensional?
Apart.
Pulling, yeah. Like you create tension when you're pulling on a rope or something. And then the footwall, like anatomy of a transform fault, is the underlying rock. So it's the one that's always underneath the other part of the fault. And then the hanging wall is the one that's over the top. Earthquakes are normally caused by this type of plate boundary, although it can be caused by other plate boundaries too. Okay, strike slip faults. Rocks on either side of the slip fault are horizontally slide past each other. And then a normal fault are decompressional forces. You're pulling apart. And then a reverse fault is compressional forces, so you're pushing together. San Andreas Fault is a slip fault. Have you guys heard of that one before?
Yeah.
It's in California.
You hear about it in movies a lot.
Yeah, like there's a movie, a very scary movie that's about it. And then Rocky Mountains, there's a lot of reverse faults. So, a little bit of a quiz review. What type of boundary does this show?
Oceanic.
Oceanic. Convergent or divergent?
Convergent.
Convergent, yeah. Because you got the two plates, one's conducting underneath the other. You got some partial melting shown by that red spot. There we go. What type of boundary is shown by this?
Oceanic continental.
Yeah.
Convergent.
Convergent, yes, because you got the subducting. If there's subducting, then it's convergent. And you got the continental volcanic arc, which would be shown in Yellowstone. You got the trench, you got the partial melting.
Transform, maybe? I can't remember. It's transform.
Transform, strike slip.
Okay.
Because they're sliding past each other. You don't have a hanging wall or a footwall. Okay, what about this one?
Try to look at my notes.
Oceanic.
They're going together, right?
Well, no, new's being created, so they're going apart.
Oh, that's divergent.
Divergent. Oceanic, divergent. Two oceanic plates, and then they are moving. You can see that because the ridge. If there's a ridge, then it's divergent.
Okay.
Divergent oceanic. Okay, now this example is kind of complicated because there's multiple. So what about right here?
That is oceanic.
Oceanic convergent.
Oceanic convergent. We're just gonna do that. And then this one,
Oceanic divergent.
OOD. What about this one?
Oceanic.
OCC.
OCC. Yep. And then this one over here,
CCD.
continental divergent. Yes. Yep. And then over here, these would be transform faults. A lot of times when you have a ridge, there's also transform faults because on a map, if you see a transform or a divergent, oceanic divergent fault go like this, and there's all these are transform faults. Got it.
So how are the Crawford cliffs made?
Huh?
The Crawford cliffs?
The bluffs?
Yeah.
That would probably be erosion from. It doesn't have a water with this because we're on like a.
Okay.
We're in the middle of it.
Yeah, I can't remember what it's called, a craton. I think we're on a craton, like a stable inner portion of the continent. So, tectonic mechanisms. We've touched on this a little bit. This is what your lab is about. Convection currents. I think you guys understand this, right? Okay. And then ridge push. This was in the book. Newly warm material floats to the top of the mantle and pushes through the crust. And then the new material displaces the old material of the plate. So it comes up and pushes. And then slab pull, the old material reaches this subduction zone over here, and it is old, dense, and it weighs a lot, so it pulls the rest of the plate into the subduction zone. Does that make sense?
Mm-hmm.
Okay. And we are done with notes. So do you guys have any questions? Does it make sense?
Does any of this apply to rivers or no?
Rivers could be formed by divergent.
Oh.
Yeah. Well, when